Hey everybody, Mr. Qualls, and today what we're going to talk about is equations that may have one solution, infinitely many solutions, or no solutions. Okay? All we have to do when we're working on these problems is solve them. Just do like we have been doing, solve for our variables, and once we get to the end of our equation, or solving our equation, the answer will tell us whether it has one, infinitely many, or no solutions. So I'm going to solve these problems and then talk a little bit about what's going on with them. Now, if we look at this, these three examples are on page 215 in your textbook. It's the 8th grade textbook, page 215. And I'm just going to take this. I'm going to start with my lines on each one of them, because that's how we do. And then when to solve this, we need to make a zero pair over here. Here we go. This is my work line. This is my zero pair. 4x equals 2x plus 16. This should be old hat for us by now, so I'm just going to keep going with this. Negative 2x. It'll leave time on the video for talking about other stuff. 4x minus 2x is 2x, and that equals 16. I'm going to make my 1. X, 16 divided by 2 is 8. So, excuse me. What this really shows us is that this situation, the only number that will work when we put into either of these to find a solution is the number 8. Now, if I wanted to do that and put an 8 into the solution, 4 times 8 minus 3 equals 2 times 8 plus 13. So I have my solution, and then I substitute it back in here to check my work. Well, 4 times 8 is 32, minus 3 is 29. 2 times 8 is 16, plus 13 is 29. 29 equals 29, x equals 8. This statement is true. Okay? It also has one solution. There is only one answer to this problem. Now if we look back at these pieces right here, look back at these pieces. Well, if I wish I had a different color marker, maybe I could use something to show if I had a different color marker. It was like, oh, well, thank you, Salty. Yeah, you're being a little more helpful today than you were yesterday. I appreciate that. So if we look at this, oh, that's pretty. Could have given me a marker that worked there, pal. But I'm okay with that. If we look at these, If we look at these right here, 4x minus 3 is really something like this. Y equals 4x minus 3, and this is y equals 2x plus 13. I hope that shows up on that video. These have a slope of 4, and a y-intercept of 3, and a slope of 2, and a y-intercept of 13. If we were to draw these two lines on, because that's what they are, is linear equations, we drew those linear equations on a graph, they would cross at 8. You know what? I should do that for you real quick. Piece of graph paper here, and I'll just draw it real quick. And let's just see if it's true, right? So we're going to go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, negative 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, negative 5, and this is 4x minus 3, so I'm going to go down to a negative 3 for my y-intercept, and I'm going to graph y equals 4x minus 3, my negative 3, and then 4 over 1 is my slope, 1, 2, 3, 4, over 1, 1, 2, 3, 4, over 1. Let's draw my line. Wow, there it is. So sound effects, and the other one was 2 plus 13. So 2x plus 13, 1, 2, 3, 4, 5. Oh man, that's a 10. 1, 2, 3, 4, 5, which is 15. This is positive 13 here, and it's 1, 2 over 1, 1, 2 over 1. Yow, I did not want to do that. So what's going to happen here is you can see if this keeps going over, these two are going to cross, but it's going to go over here. Now, my graph isn't big enough to show it, but as this goes up, you can see these things are going to cross out here somewhere, and I bet since x equals 8 in my original problem, that's what's going to happen. 5, 6, 7, 8, little dance number. And if we went all the way up like this, and we extended our graph a little bit, la 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 la, and we extended our graph, because I have more paper here, and if we extended our graph, we went all the way up here like this, and we took this one out, it's going to cross right up here. When that thing goes up there, and that's up there, it's going to cross right there, which is at x equals 8. So, that wasn't the prettiest example I've ever made, but it's going to cross at 1. Now if we keep this on the second example, we need to bring this down. We need to distribute this. 4x minus 2 minus 3. 4x minus 5 equals 4x minus 5. Oh, look. If I make a 0 pair with my x's, negative 5 equals negative 5. Well, when is this true? Always. That's right. So if this is always true. So this statement is true, and it has infinitely many solutions. It's infinitely many solutions because if we look at this again, and we put 4x minus right here, negative 5, y equals 4x minus 5, negative 5 y-intercept 1, 2, 3, 4, 1, 1, 2, 3, 4, 1, and I draw this picture here, and then, oh look, it's got the same slope as that other one because they were parallel. Yeah. And if I look at my second line, which is 5, and I put negative 5 here and then go up 4 over 1, up 4 over 1, it's the same line. So these two lines are going to have the same drawing with them, and they're going to share an infinite number of points that are true for both of them at the same time. Okay? So this one is true, and there's the 4x minus 5, but it has an infinite number of solutions. We could put any number in there that we wanted to. 1 times 4 minus 5 is negative 1. 1 times 4 minus 5 is negative. Negative 1 equals negative 1. If I put a 0 in there, negative 5 equals negative 5. That's always true. If I put a 2 in there, 2 times 4 is 8 minus 5, 3. 2 times 4 minus 5 is 3. 3 equals 3. That's always true. Okay. Here's my next piece down here. Now we can see, if we know what we're doing and we've been paying attention, are parallel to each other. And I already have one of them drawn right here, this black one right here. The other one is this, 4x plus 2. And if I did a y-intercept here, 1, 2, 3, 4 over 1, 1, 2, 3, 4 over 1, and I drew this line, they are parallel to each other. The two black lines are parallel to each other. They're never going to cross. Just like these are never going to cross. They're never going to be true. And if I subtract 4x from each side, 0 pair, 0 pair, 2 equals negative 5. When is that true? Never. That's when that's true. So this has no solutions, and it's a false statement. This one's true in one place. This one's true everywhere. and this one is false. Okay? So, let's look at something that's on page 219 in the book. This thing reads that the Dig It project, can you dig it? That's a movie reference from late 70s, I think. Movie's not for kids, probably shouldn't watch it. Dig It project is designing two gardens that have the same perimeter. One garden is a trapezoid whose non-parallel sides are equal. The other is a quadrilateral, and two possible designs are shown. So what they want to know is, can we put any number in here for x? If we choose 1 foot for x, or 2 feet for x, 3 feet for x, is this going to work? So what we need to do is we need to put all of these together and set them equal to this and see if that's going to work for us. So we're going to total these sides. So I have 2x minus 2 plus x plus 1 plus x plus x plus 1. And if I put these together, and I'm just going to do my work over here, this isn't standard stuff, but I'm just going to make this go. I've got 2x, 3x, 4, 5 x's. And then over here I have negative 2 plus 1 plus 1. So 1 plus 1 is 2 minus 2 is 0. So this whole side is 5x. This whole thing totals to 5x. And that's a parameter on that one. If we look at this one, it's 2x minus 9 plus x plus 8 plus x plus 1. 2, 3, 4, 5x. Ooh, that kind of bodes well because a math person probably put this together. 9, negative 9 plus 8 plus 1. This is totals 9. Plus 9 is nothing. So it's 5x equals 5x. So 5x equals 5x. When is that true? Always. So this one has an infinitely many solutions. Any number we put in here is going to work. 1, it'll be 5 and 5. 2, 10 and 10. 3, 15 and 15. 4, 20 and 20. It matters. Okay? Every single number that we put in there. However, only positive integers. Because if I put a 0, I guess it's still true. But we're not going to, if this is a perimeter garden. If I put a negative 1, now we have negative 5 feet, negative 5 feet. If I put a negative 10, negative 50, and negative 50, I don't think we're going to be building anything that has a measure for a perimeter. If you can, I'd really like to see it. The last thing I'd like to talk to you about today is this problem. It's number 2 on the 7-4 worksheet that I've got online for you. All you have to do is work these things one piece at a time. Now, I have a 2 on the bottom of this fraction, and there's a 2 on the bottom of this fraction. We could just pretend that this is just one thing that's being divided by 2. And then multiply both sides by 2. Get rid of the fractions. 2 times 1/2 is 1, and 2 times 7 is 14, equals 2. Well, what do I do here? I mean, are these separate things, or are they just one thing? Well, it doesn't really matter because this thing is being cut in half, and it's going to be multiplied by 2. So those things undo each other. So this is just going to be n plus 14, and look at what happened. Okay? Also, if this had started off like this, equals n plus 14 over 2. Well, this is just n divided by 2 plus 14 divided by 2. So let's just make this n over 2 plus 14 over 2. And then this is either 1/2 n, or you go ahead and multiply everything by 2 and end up with n plus 14 equals n plus 14. Or realize that this is 1/2 n plus 7, and n divided by 2 is really just 1/2 n, and then 14 divided by 2 is 7, and here you go again, and they have an infinite number of solutions. Okay? So I guess my point in talking about this is work it and see if it happens. Don't just I don't know what to do with that, so I'm not going to do anything with it. Try to think about what's going on. We want to get these things right. not just get them done, right? And a lot of us that are used to just like, well, what's my answer, or just show me how to get the answer. What we really want to know is, how do these things work? And if I can group things on the top and realize, well, this is just being cut in half. If I double it, it's going to be itself. Think about that kind of stuff. All right? I know some of these things are difficult, but just work through them, get what you can done, and I'll have some new stuff for you on Monday. New instruction on Monday. Thank you.